Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this playlist, we've seen a lot about the cohomology of coherent sheaves on curves. In this video, I want to talk about sheaf cohomology in higher dimensions. And what I'd like to do is not so much present the theory of how it's built up, but rather all the basic facts that algebraic geometers use to work with cohomology. So what's our basic setup? To keep things simple, XE is going to be a quasi-projective variety over an algebraically closed field K. And mainly we'll be looking at the category Co-X of coherent sheaves and the category of quasi-coherent sheaves, Q-Co of X. But the definitions, I guess, work more generally in the category of sheaves of abelian groups, which I'll denote with SHX, okay? So all these categories, they're abelian categories, so you can talk about direct sums and also kernels and exact sequences. And the theorem that allows you to define cohomology as Grothendieck set it up is the following theorem of his, and this is where a lot of the abstract machinery comes in, is that if you look at these two categories, either the category of sheaves of abelian groups or quasi-coherent sheaves on X, they both have enough injectives, okay? So that means that we can define derived functors, okay, of the global sections functor, okay? So remember what the global sections functor is? It's often denoted as H0X, and then you can put in here either a sheaf of abelian groups or a quasi-coherent sheaf. And it just means that, remember, this is a sheaf, so it assigns to every open set and either an abelian group or a module, okay? And in this case, you want to put in the open set, which is the whole of the X, okay, that you're looking at. Okay, so this is the global sections functor, and you can take the derived functors, which I'll denote by HI, and then the X here is optional. If it's understood, I'll leave out that X. So if you input a sheaf of abelian groups in here, it'll spit out an abelian group. And if you input instead a quasi-coherent sheaf, it will be a vector space over K. And actually, it's not like two separate derived functors here, okay? If you have a quasi-coherent sheaf, you can use this one, the definition here or the definition here, you'll get the same answer, okay? So the most important thing about this is that even though when we define these derived functors, the basic idea of what we do is we replace the sheaf, this F, with a resolution, an injective resolution, a resolution by injective sheaves, okay? And then we look at the global sections of that and the cohomology of that. And usually it's almost impossible to compute what that injective resolution is. So actually when algebraic geometers work with cohomology, they don't do it this way. They use the theory that's set up and all the basic facts that I want to present to you now. And the first one that immediately comes from the general homological algebra is if you have a short exact sequence of form like this, f 0 to f prime to f double prime to 0, then you get a long exact sequence in cohomology. So this global sections functor, it's left exact. Okay, so you start from 0 and then you have h0 of f prime to h0 f to h0 f double prime, but you can continue this to a long exact sequence by going up to h1 of f prime, h1 of f, and so forth. Okay, so that's rather good. So this is one of the key reasons why you want to have a cohomology, is because this term here essentially gives you the obstruction to lifting a global section on this quotient f double prime to a global section of f. Okay, that's the key reason. Of course, to study this well, you need to also understand H2 well and so forth. Okay, so what are the basic facts which allow you to really work with cohomology? So the first one, due to Grothendieck, is Grothendieck vanishing. We've seen a version of this for curves already. When we looked at curves, you only had H0 and H1. So the dimension was 1, and that's the reason why you only have to look at H0 and H1. H2 and higher cohomology vanishes. Okay, so more generally, suppose you have F is a sheaf that's supported just on a subvariety Y, and this Y has dimension D. Then if you look at HIX of this sheaf F, this will vanish whenever this I, the index of the cohomology, the degree of cohomology is bigger than the dimension of this, the support of this F. So that's the first very nice result that you have. The second thing is that, well, the global sections functor is going to be exact if you look on affine schemes. So you would expect that if you look at cohomology, if you look at affine schemes and you consider the quasi-coherent category, the category of quasi-coherent sheaves. So that suggests the following fact. Suppose you have F is a quasi-coherent sheaf, then HIXF is going to be 0. The cohomology vanishes for I greater than 0. Okay, so that's as soon as X is affine. And when you're looking at the cohomology of a quasi-coherent sheaf, then all the higher cohomology vanishes. You only get H0. So the next thing is that if you do want to compute it, one of the fewest ways you can do it, and that's what I did in my video previously, is use Cech cohomology. So this is the only time you can compute it, okay, really, sensibly. So if F is a quasi-coherent sheaf, then this HIXF can be computed using Cech cohomology. Okay, that's rather nice, and we saw how to do some of that for some sheaves on PN, in fact the line bundles on PN. Another essential result that we saw for curves is Serre finiteness and vanishing. Okay, so the situation where this applies is firstly where X is a projective variety and F is a coherent sheaf. Okay, so these are both important things. The X being projective basically means that you're in the compact situation. When you look in the class of these quasi-projective varieties, you're in the compact situation, and then coherent here means that you're kind of in this finite setting. So it's a very, very finite situation. So what does the finiteness refer to? Okay, so suppose you look at this HPXF, this cohomology group. Okay, so it's actually a vector space over K, and you talk about its dimension. Okay, and this dimension is often denoted by this little HP rather than the big HP. Okay, this dimension is going to be finite. So all these cohomology spaces are finite dimensional. Okay, so the next thing is a Serre vanishing. Okay, so remember something that's extremely important is that we have situations where we can guarantee that cohomology vanishes. Okay, so that's one of the things, because the cohomology is in many ways an obstruction. Okay, so when it vanishes, that means there is no obstruction and we can lift. We saw examples here of Grothendieck vanishing, but that only works if this I is large enough. Okay, so we want something where preferably we can control how H0 behaves, so we want to have even vanishing of H1. And Serre vanishing gives us an example of that. Okay, and what it involves is something called the Serre twist. So firstly, suppose we have some finite map from X to Pn. Now remember, X is a projective variety, so you've always got an embedding of X into Pn, so that's an example of a finite map, okay? And that's the usual one that one would consider, okay? So given such a finite map, you can have what's called a Serre twist, okay? So given any integer m, okay, so firstly, on this Pn, you can look at this line bundle or invertible sheaf OM. You can pull that back up to invertible sheaf on X, and tensor that invertible sheaf with its F to give you a new coherent sheaf, F twisted by M. Okay, so that's the Serre twist by M. Well, it turns out that if you make this M big enough, so for all M sufficiently large, so after a certain, as long as M is bigger than a certain constant, okay, you can guarantee that all the higher cohomology, this HI of these FMs is equal to 0. Higher cohomology just means that I is greater than 0. So this is a wonderful result. Okay, it even means that here H1 will be equal to 0. The only thing that's a little bit annoying is that, well, this is only true for M large enough, and you don't have direct control over how big that M needs to be. Okay, from the statement of the theorem. Okay, so this is telling you what's going on for I greater than 0. What happens for I equal to 0? Okay, for H0 of Fm, well, in that case, the global sections of this Fm capture a lot about Fm for this M large enough. Okay, so if you have M large enough, what do you have? Well, in this case, suppose we look at H0 Fm tensor O. Okay, so this is a vector space tensor O. So this is a finite dimensional vector space, say of dimension R, and then this tensor with O. So this is a tensor over K, just means K R copies of O. Okay, that's what it means. Okay, so that's a vector space tensor over the field K with this O. Okay, then if this is R dimensional, that means just R copies of that. Okay. So what happens here? So what is this map? There's a map I claim from here. Okay, so this is a direct sum of copies of O to Fm, and it's actually surjective. Okay, so in this case, when M is big enough, this Fm is just a quotient of a finite direct sum of copies of O, and we can say how many it is, and we can see how that works. So what is this map here? Okay, so the map is the following. Remember, what is an element of this H0Fm? This is a global section, but one way to think about this is it's just a morphism from O to Fm. So if you take that morphism, you can apply it to any section of O to get a section of Fm. Because what does morphism from O to Fm mean? It means it takes sections of O to sections of Fm. And it turns out that this will be surjective. Okay, so this is also a very, very important result. And even though you may think, well, it's only this bit here says that Fm is really nice for large M, but what it means is that, well, you still get a surjection when you apply the category equivalence, which is tensoring by O minus M. So it also says, for example, that for any sheaf F, okay, it is a quotient of a finite direct sum of copies of O minus M, as long as M is big enough. Okay, so that's another way you can use this result. That's very, very important here. Okay, great. So that's Serre finiteness and Serre vanishing. And we've seen both these in the case of curves previously in this playlist. So there are some of the basic facts that I use to work with cohomology. And one of the things that we get out of cohomology, and this is one way to perhaps think about what it does for you, is it gives us lots and lots of numerical invariants. Okay, so these HPs, these little HPs, the dimensions of these cohomology groups, okay, they really tell us a lot about coherent sheaves and also about geometry. And I want to show you an example of that through the Euler characteristic and the Hilbert-Serre polynomial. So the other thing that the machinery sets up for you is the fact that there are a lot of nice formulae that can be applied to help you work with these invariants. And the ones which are easiest to work with, these HPs in general, are a bit harder to work with. But if you look at the alternating sum of them, okay, that's the Euler characteristic, that's a lot easier to work with. And more generally, we can work with what's called the Hilbert-Serre polynomial. So rather than looking just at the Euler characteristic of F, you can look at the Euler characteristic of all the twists of F. Okay, these are the Serre twists that occur in here. And so depend on this finite map, okay, here. Okay, you can look at all the Serre twists of that. And now we think of this as a function of n, okay, where n is an integer. And that's called the Hilbert-Serre polynomial because it turns out to actually be a polynomial, and we'll say some things about this. Okay, so why are these things easier to work with? So the key point is that just from the fact that you have a long exact sequence here, okay, if this eventually goes to 0, and by Grothendieck vanishing, after a while, you'll just get a string of zeros at the end. You can look at the alternating sum of the dimensions, and that will be 0. Okay, so that's something that comes straight away. Okay, just from the long exact sequence. And that also means that if you have such a short exact sequence of coherent sheaves on my projective variety X, okay, so I can define both the Euler characteristic, these are HPs and these things here. Okay, so note that this sum, this alternating sum, is a finite sum because all these terms by Serre finiteness is finite, and also by Grothendieck vanishing, this sum goes from I equals 0 up to just the dimension of in fact, the support of F. Okay, so these are finite sums here and they're well defined. So firstly, chi of the middle term, chi of F, is the sum of the Euler characteristics of the outside terms, chi of F prime and chi of F double prime. And if you do this for each of the twists of F, another way, another thing that you can see is the Hilbert-Serre polynomial of this middle term, F, is just the sum of the Hilbert-Serre polynomials of the outside terms, h of F prime, h of F double prime. Okay, so this is all sort of numerical data that you can associate to this F. And what's really nice is that this data has geometric meaning. Now, some of it is a bit easier to see than others, and I wanted to show you an example of one which is very, very easy to see. Okay, so we're going to look at this hfn, and it turns out to be a polynomial. It's going to be a polynomial function of this n. And so one thing you might want to look at is what's its degree. Okay, well, it turns out the degree, it's going to be something, and it tells you something about the geometry, okay, and something about this sheaf f, okay, this coherent sheaf f. It's just the dimension of that sheaf, the dimension of its support. Okay, and I don't want to prove this, but I want to give you the flavor of how you go about proving it, so that you can see at least why it's true. Okay, and it's kind of natural to kind of assume that it is true. Okay, so the first thing is that you can prove this by induction on the dimension. That's the first thing to note. Okay, you use induction on the dimension. So if the dimension is equal to 0, it's quite easy to see. This f has to be essentially just a extension of skyscraper sheaves. Okay, so you're just looking at O of a point, and then you can by this property here. Okay. This property here, the Hilbert function of a sheaf, can be given by the sum of the Hilbert function of a sub-sheaf and the corresponding quotient. Okay, that means that you just have to check this for the skyscraper sheaf, and then for the skyscraper sheaves, you can use Grothendieck vanishing to see that you just get H0, and to compute H0, it doesn't matter how many times you twist a skyscraper sheaf. Okay, if you tensor it with any invertible sheaf, you just get that skyscraper sheaf back by isomorphism. So chi of that is just H0, so it's just the constant 1. So you're getting constant polynomials there, and that's degree 0. Okay. So in general, what you can do, this takes a little bit of analysis, but you can reduce the case by similarly looking at filtrations of f to the case where you more or less just have the structure sheaf of some subvarieties at y. Okay, you actually have to use the Serre, this second part of Serre vanishing. Okay, so you may have to twist this structure sheaf of OY by some amount here. Okay, but that's not going to change things. So what are we going to do now to try to show that we get a polynomial, and the degree of that polynomial is indeed the dimension of this f. Okay, so we're assuming f has this form here. It's the structure sheaf may be twisted by some number. Okay, so all we'll do is remember you're working with a map like this. Okay, and you can take a hyperplane inside this Pn and you pull it up. Okay, and that gives you a hyperplane H inside X. And you can get lots of different hyperplanes. So you can assume that this hyperplane actually doesn't contain your Y, so it cuts it down. Okay, in dimension. Okay, so we're going by induction on the dimension of this f, and hence the dimension of y. The dimension of f is just the dimension of y here. Okay, so we'll take that hyperplane, and that gives us immediately an exact sequence like this. OH is going to be a quotient of OX, because H is just a subset of X. So you just basically take this structure sheaf and you mod out by the ideal of regular functions which vanish on H, so that's OX minus H, and that's what you have here. Okay, so this minus H is essentially just minus 1. Okay, so that's the key point. So what you can do now is that you can just tensor this with f to the n. F to the n. And what do you get here when you tensor by f to the n? Well, it turns out because of what f is, okay, so maybe we'll work with the easiest one. When you tensor this with f to the n, you just get this here. When you tensor this by f to the n, you get f to the, since this is essentially minus 1, f to the n minus 1. When you tensor this with f to the n, well, this is tensor with OH, so you basically restrict the sheaf to H. So this is f restricted to Hn. So if you think about what this sheaf is, you take this sheaf here, okay, you twist it by n, so you get OYM plus n, and you're going to restrict it, that's in y at the moment, you're going to restrict it to H, so basically you're now got the structure sheaf on y intersect H. So that'll be some one codimensional subset of this y. So it'll be a hyperplane cut in this y. So you've cut it down by in dimension by 1 here. Okay, so that's what you have here. And just because of the situation that we have here, because this cut set as a hyperplane, this will actually be injective. So that's something I don't want to check. Okay, so there's a lot of little details that I haven't checked here, but now the bit that I really wanted to tell you is how we get the fact that you get a polynomial, because we're actually here home free, okay? So what we do now is we have a look at this function of n, okay? So if you look at the Hilbert-Serre polynomials, you look at the chi of this, so that's going to be hf of n. And if you subtract chi of this, you get the chi of that. So the chi of this is hf of n minus 1. So this function of n, you look at it, evaluate at n and n minus 1, you take the difference. And what you'll get is you'll get this h of f restricted to h n. So this is Hilbert-Serre polynomial of a sheaf that's now supported on y intersect h. So that's of 1 degree lower. So we can use induction to say this is a polynomial of degree d minus 1. And now this is a function on the integers. This hf is a function of the integers, such that when you evaluate at n and n minus 1 and take the difference, that's a polynomial of degree d minus 1. And the only way that that can happen is if this here is actually a polynomial of degree d. And one way to kind of see what happens and why that's true is essentially, well, this operation, you can think of this looking at this function, hf, you evaluate it at two consecutive things, n and n minus 1, and when you take the difference of that, this as a function of n is like applying a discrete version of a differentiation operator to get you down to this polynomial of degree d minus 1. So if you apply a discrete version of the integration operator, you can recover this original function, and it will have to be a polynomial of degree d. And essentially the only fuzziness is, of course, if you change each of these by some constant, okay, that'll give you the same discrete derivative here. Okay, so this is the key reason why this is true and why I expect this theory to give you this type of result. Okay, I hope you enjoyed this adventure in pure mathematics.